molecular orbitals. So you learn all those. And the symmetry, you learn all this. And a little bit of computational chemistry, it's going to be fun. I'll give you some systems, some molecules to calculate. Right, like, carbon 60. Soccer ball, right? Soccer ball. How many vertices? You guys know how many vertices? How many faces? Soccer ball? 12 pentagons. 12 pentagons. But there are also hexagons, 20 hexagons, a total of 32 faces, a total of 60 vertices. Well, 60 carbons in fluorine. And we'll look at that as well. It's a soccer ball, it's spherical shape. And actually there are 60 pi electrons, conjugation. Okay, conjugate, 3 electrons. 3 electrons rotate about this field. Or just use our 3-dimensional rotation model to hand calculate, the whole it's basic. But again, now we're doing a Gaussian calculation, or if you like Spartan, I don't care, they give you the same numbers. And we compare our results, see if they give you the same result or not. Or we can design some different novel molecule. We can have carbon has performed sp hybridization, right? Pi conjugation to pi bonds. What if I do this? Okay, you have a 2-dimensional wave. You have your electron to rotate. I'm assuming there are 3 electrons. It's conjugation. You have a big pi bond. Actually, you have 2 big pi bonds. 1 pi bond is like you have p electrons pointing towards you, right? Some carbons, maybe 16. So you have 16 p pointing towards you. But then you have another 16 that's in the plant. That's in the plant. Oh. So you get the idea. You get the idea. I'm not going to show all 16 p orbitals. We have 16 in the plant, you have 16 pointing towards you, and we can look at the 16 p orbitals that point towards you. So you have 16 electrons. Well, they will occupy 8 orbitals, and then use 2-dimensional rotation model. Okay, 2 electrons occupy the ground state, and then 2 electrons occupy the first excited state. And you will need to take care of the degeneracy. Because in the ground state, the rotation energy is rotation. Remember, the rotational energy can be 0. The rotational energy can be 0. So the ground state corresponds to 0 rotation energy. So just 1 orbital. M sub L equals 0. The quantum number is 0. But the first excited state, you have plus or minus 1. Plus 1 or minus 1. The rotation energy for 2-dimensional, it's M sub L squared times h bar squared divided by 2i. Okay? Memorize this equation, please. It's not so difficult. It's not so difficult. So for a 2-dimensional rotation, you have ml squared times h bar squared over 2i. For a 3-dimensional rotation, you have L times L plus 1 h bar squared over 2i. And this L, well, if you're talking about the electron, it's just the angular momentum quantum number. For a diatomic molecule, sometimes you see J, just by convention. When we describe the rotation of a diatomic molecule, we often use J. When we are describing the rotation of the electron, we often use L. But same thing, right? They represent the same thing, the quantum number of the rotation. Basically, you just need to remember this part, right? H bar squared over 2i. H bar squared over 2i. And again, if you look at this, when M sub L equals 0, you get the ground state, the rotation energy is exactly 0. And then M sub L can be plus minus 1. And you have the 2 degenerate orbitals. Okay? And they have exactly the same energy, h bar squared over 2i. If it's 2-dimensional rotation, if it's 3-dimensional rotation, you use this rotation. Okay, we'll talk about those. And after this computational chemistry, we'll do something about statistics. I really hope we can have a 200 level probability in the statistics class for this tension problem. The biology department has one. Right, you guys stop majoring. They do, right?
Yeah.
200 level, right?
Well, they just teach it grade one, but
Okay.
they just teach it over the whole quarter instead of like just for 6 weeks.
Okay, I see. We have to know something about probability. Because if I give you 1 mole gas molecules, and then I ask you to give me the average translational energy, you know it's 3/2 kT. You know that, but I'm going to show you how to get that 3/2 kT. I will treat the system as a particle in the box system. I'll look at just 1 molecule out of 6 million, whatever molecule. I just look at 1. And I have this energy levels, translational energy levels. N squared times H squared divided by 8mA squared. Of course, I'll give you the dimension of the box. I'll give you the pressure, I'll give you the temperature, and then use those information, you get the energy levels of that molecule. And then what I will do is I will assume, all other molecules have the same energy levels, and then I will start to put those molecules in those levels. And how to do that? Intuitively, we assume that all molecules occupy the ground state, the lowest energy state. That will give you the lowest energy. But that's not true. We need to obey this so-called Boltzmann distribution. At a finite temperature T, like room temperature, all molecules move. And these energy levels will be occupied in a way that lower energy level have larger population than higher energy level, right? But you cannot say it's all molecules occupy the lowest energy level. Other energy levels, they all accommodate molecules, more or less. The higher energy, the fewer molecules. The lower energy, the more molecules. And then after I do that, after I distribute the 6 times 10 to the power 23 molecules on all those energy levels, and then now we can use this probability. We can take the weighted sum of the translation energy. We can calculate the average translation energy. You'll see, in the end you'll get 3/2 kT. For this 2-dimensional world, again we have, let's say, 1 mole molecules. And we'll have to imagine all of those molecules rotate in a 2-dimensional plane. Well, that's impossible. Okay, that's not real. It's imaginary. Let's say we are looking at a 2-dimensional world. So all molecules can only rotate on 1 2-dimensional plane. In the end, you'll see that the average rotation energy for that 2-dimensional molecule will be just kT, ½ kT times 2, because it's 2-dimensional. 3-dimensional, you may guess, well, 3/2, that's correct. 3/2 kT. Vibrational, a little bit difficult, depending on what molecule you're looking at. If you are looking at just HCl, there's only 1 possible vibrational mode, or we call it stretching, right? We call it stretching. And then, but hey, if you have water, water is like this. Well, there are 2 possible stretching, right? Symmetric and asymmetric, right? This symmetric. Asymmetric. There's a 3rd one, bending. So you'll see 3 peaks. You'll see 3 peaks in the pi-r spectrum of water. All right, and then when you go really large molecule, how about a protein? If you have a protein molecule that consists of 1,000 atoms, okay, 1,000 atoms will have 3,000 coordinates. Each one has x, y, z, x, y, z, x, y, z, x, y, z. 3,000 coordinates. So the motion, the number of motions of this molecule will be 3,000. 3 of them, 3 out of the 3,000 is translational. The whole molecule moves this way. Imagine we have a large molecule move this way, or this way, or that way. And also 3 rotations. Rotate about x-axis, y-axis, and z-axis. The remaining 3,000 minus 6, that's 2,994. All other motions are vibrations. Okay, that's crazy, that's crazy. Nearly 3,000 vibration modes. Some involves the stretching of a bond, some involves bending, some involves torsion. So what is a torsion? If you look at a simple molecule, C2H6, C2H6 ethane, we have two methyl groups. Remember, staggered conformation, eclipsed, let's say this is eclipsed. Okay, I have 5 hydrogen atoms, each has 5 hydrogen, right, eclipsed, and staggered. And then, well, I don't know. It's my hand, my 5 hydrogen atoms, so it doesn't have enough. But for ethane, you have those torsion, which is to change the vacuum angle we're talking about there. And also, we'll look at we can calculate the average vibration energy for a protein. Vibration energy will be much larger than a diatomic molecule, simply because it has a lot more vibrational modes. And then we'll further connect quantum chemistry to thermodynamics. Once you can calculate the kinetic energy and potential energy, you get internal energy. And also, we can use the results to calculate the heat capacity and constant pressure, constant volume. We can calculate enthalpy. And then we'll calculate entropy, so that we can get Gibbs energy. And what's the definition of entropy? The measure of, what's that word? Disorder, measure of disorder. Or chaos, whatever. So, but that can be calculated. Now there's a simple equation, which is K times Ln times, well, K, the Boltzmann constant K sub B, times the natural logarithm of the total number of states. When you have 1 mole molecule, the total number of states will be huge. Okay, how huge? It's like 10 to the power of 10 to the power of 23, that huge. Okay, 10 to the power of 10 to the power of 23, that huge. But you take logarithm of that. So, and then the entropy does not look that huge. You take natural logarithm of that huge number, and then you multiply that number by K. K sub B is a small number. It's 1.38 times 10 to the power of negative 23 joule K. So in the end, you will get a reasonable number for this entropy. And I think that's the plan of this whole semester. And I want to talk about the quiz question. For the quiz question, it's easier. You just, so here's the trick. I would just treat this as alpha, or treat this like beta. Okay, so that you don't have to spend a lot of time writing the whole expression here. So E naught is simply half H mu minus, this is alpha, right? And E1 is 3/2, right? So without this anharmonic correction, it's just 3/2. And then minus, so plug in this n equals 1 here, you get E2 equals, how many alpha? 5/2. This squared. Right? And we look at the energy spacing. So when you look at energy spacing, that's a difference between two energy levels. And when you are taking UV spectrum, IR spectrum, very often you're taking the energy difference. For example, IR absorption from level 0 to level 1, and you get, there's one IR photon absorbed by the molecule, so that it can be excited. So you're looking at the difference. So if you look at the difference between these two, you just take the difference. The difference will be alpha minus, so this guy minus this guy, 2 beta. Does that make sense? This minus this, you get alpha. This minus this, you get 2 beta, but there's a negative sign. Right? Now, E1 to 2 equals, so this guy minus this guy, still alpha. And this guy minus this guy, what will you get? Wow, very good, very good. Apparently this is smaller than this, so energy spacing decreases. Okay. So this is the spacing from 0 to 1. So this guy is alpha minus 2 beta, and this guy is alpha minus 4 beta. Does that make sense? And then alpha minus, how many beta? How many beta? Well, I would assume that this is 7 minus 49 beta, and 49 minus 25, that's 24, right? 24 divided by, that's smaller. Okay, now we beta, and smaller, right? So, actually my point is, I want to illustrate this. The actual vibrational energy level, spacing, decreases as n as a quantum number increases. And in the end, it will dissociate. At this point, it will dissociate. And we can actually draw a conclusion if somehow we can make this diatomic molecule vibrate faster and faster. That means excite its energy level from 0 to 1 to 2 to 3. It keeps absorbing energy. In the end, it will decompose. In the end, it will decompose. The bond will break. Okay? And above this point, the energy will be continuous. You have two separated atoms. You have two separated atoms. They are no longer combined. The energy spectrum will be continuous. Will be continuous. All right? Does that make sense to you? Okay, cool. A so-called thermal reaction is simply to provide thermal energy, that is the surrounding. So you heat up a flask. In the flask, you have your reactants dissolved in a solvent. And you heat up, really you're heating up mostly the solvent molecule. So those solvent molecules move really fast, and they will collide into those reactants. Say this is a reactant. And I have solvent molecules. A lot of solvent molecules surrounding this reactant. And after many collisions, sometimes the reactant loses energy through the collision, but since you are heating the solvent up, so higher temperature, then on average, this reactant will get enough energy, so it goes up and up and up and up and up, and in the end, it accumulates enough vibration energy right here, so it's right before the bond breaking. And then, final push from the solvent, maybe it decomposes. Now we have two separated atoms. All right, so that's a quiz question. And you'll see this equation again in assignment here. A follow-up question. So we look at this equation again. And if I give you the spacing, so for example, if I tell you the spacing, and I give you this nu, would you be able to calculate the bond energy of the molecule diatomic? It's a diatomic molecule. Let's make it easy. It's a diatomic molecule like HCl. If you are given this nu, okay, I don't remember what the nu is, but I just remember the wave number. That's around 29. And you can calculate the frequency from the wave number easily, right? The frequency is just wave number times the speed of light. So this guy times the speed of light. That's about 10 to the power of 14 hertz, roughly. 10 to the power of 14 hertz. Okay, because right? And I'm using SI unit right now, so roughly. Okay. So if I give you this wave number, I give you the wave number, and also I give you this energy spacing. So either this spacing or that spacing. I guess this is an easier one. So I'll give you this energy spacing. Were you able to calculate the bond energy if you look at this point? What do you think? So it's like I tell you this alpha minus 2 beta equals something like this. So these two pieces of information, will you be able to calculate the bond energy? Actually, the answer is yes. The answer is yes, because this alpha is h nu, right? We define this alpha to be h nu. We define this beta. I think it's one of the homework questions. So this is alpha, this is beta, and you're given the energy. And because I give you this nu, so I give you this nu. So this is known, h nu is known to you. H nu is known to you. There's only one variable here, d sub e. Right, so you can easily calculate d sub e. And d sub e will be d. Okay, so that's it. But we're not done yet. And what's that? Can you tell me why this d sub e is not the bond energy? So this is defined to be d sub e. From here to the bottom, d sub e, but it's not the bond energy. How come? Oh yeah, very good. So what we want to do is actually we want to do this, and this is called d sub 0. So use d sub e minus that's the little part. The 0 point energy is called 0 point energy, and then you get d sub 0. D sub 0 is exactly the amount of energy you require to break the bond. Okay, so that's about this one of the homework questions. Again, here's the bad picture on the screen. You can see the difference between d sub e to the bottom, d sub 0 to this so-called 0 point energy. And this 0 point energy is not half h nu anymore, it's half h nu minus 1/4. 1/4. This has 1 times this beta correction. Okay. Any question about this? And again, this red curve is a real diatomic molecule. This yellow curve is a harmonic oscillator. Harmonic oscillator. The red one includes anharmonic correction. Anharmonic correction. Next week, next Friday, you're going to measure the IR spectrum of each CL and DCL. You will actually see this kind of behavior in the equations. Right? And at the end of last lecture, we mentioned that not all vibrational transitions are allowed. The transition probability is proportional to the square modulus of this quantity. And this quantity is called transition dipole moment. We know what the transition moment is, what a dipole moment is. This is called transition dipole moment. Because in this equation, you can see you have a ground state wave function, you have an excited state wave function, and you have the dipole moment in the middle. And now I'm going to quickly show you why this is useful. Last time, I think I gave you an example of hydrogen atom. This time, I'm going to show you the mathematical proof why the 1s to 2s transition of the electron is forbidden So you have a nucleus, and let's say this is R, you have the electron. And I want to tell you that it's possible to define the dipole moment even for a single atom. So we're looking at this diapole. Why? Because you have positive charge, you have negative charge, they are separated, the distance is R, so I'm going to define this dipole moment. This, right? The charge times the distance between the positive charge and the negative charge. All right? And we haven't learned the hydrogen atom yet, but I think I can tell you this. The 1s orbital is quite simple, e to the power negative r. 2s, 2 minus r, e to the power negative r over 2. All right? And these two are orthogonal to each other. Okay, that's a whole lot of other derivation. There's a theorem. The Hamiltonian of a molecule, which is the total energy operator. If you apply this Hamiltonian to a molecule, you'll get more than one solution. Sometimes you'll get an infinite number of solutions. So that means you'll get an infinite number of eigenfunctions. And if those eigenfunctions have different eigenvalues, they are orthogonal to each other, which means the integral of the product of these functions is 0. This guy means complex conjugate. This guy means complex conjugate. And I think I skipped derivation. I'm going to show you the result. If you put 1s orbital here and put asterisk here to make a complex conjugate of this function, and then multiply by this r, e times e, and then multiply by 2 minus r, and then e to the power of negative r over 2. You integrate this, that will be 0. That will be 0. And this 1s asterisk is simply the complex conjugate of this guy. So this guy is 2s. This guy is 1s. This guy is dipole moment. Any question about this expression? Any questions about this expression? So it's like this transition dipole moment equals, I'm sorry, this two, one of these two is ground state, one of these two is excited state. It really doesn't matter. It really doesn't matter where you put this asterisk, as long as you have this dipole moment in the middle. And we'll prove this. I hope you guys bear with me. It will try to quickly prove this. It's a triple integral. It's a triple integral. I hope I can make it easy enough to look at it. I'm going to prove this to be 0. Okay, because we need to integrate both x and y and z. It's a 3-dimensional world. Okay. And this guy is a vector. This guy is a vector. So I guess, I don't know, have you ever seen, a vector in a triple integral before in your calculus class? You've done this kind of thing?
That's Cal 4.
Oh, that's Cal 4. You did that?
Yeah.
Cool. Basically, you need to decompose this. You need to decompose this R to make it even more complicated. So I'm going to take this E out first. It's a constant, okay? And then we're going to decompose this R, xi plus yj plus ck. Are you okay with this? This R is a vector, and that's the coordinate of this E, but then it can be decomposed. We project it to x, y, and z. You get x times the direction in x, y times j. Any question about this? I just decomposed the vector R. R is just x direction in y direction and z direction. This guy is simply just R. Right? Okay, you're okay with it. And then we have to prove that this guy can be separated into 3 triple integrals. Okay, that's even more complicated. But one of those two is one of the 3 is just x. Okay, I'm gonna prove that in the x direction it's 0. And similarly, it's gonna be 0 in the y direction and z direction. Does that make sense? I'm trying to prove that this integral is 0 in the x direction. Are you okay with this or not? Cool. And then I want to show you that although it's a triple integral, you just need to evaluate this with respect to x first, and you'll find the value is 0. Because this guy is an even function of x. This guy is an even function of x. Why it's an even function? Because r equals x squared plus y squared plus z squared. So if you change the sign of x, how does that affect r? No effect. So if you change the sign of x, you don't change r, you don't change the function of r. So they are even functions. But look, in the middle, you have an odd function. So basically, you're looking at an even function times an odd function times even function. And you integrate this with respect to x. Even function times odd function times even function, the product will be even function or odd function. Even times odd times even. That means if you change the sign of x, this guy no change. This guy no change. So still positive. This guy change sign. This guy no change. So no change, that means multiply by 1, right? Change sign means multiply by -1. So what's the product of those 3 functions? Even or odd? Odd function, very good odd function. And, okay. And now, if you're integrating an odd function, what's the result? Let me show you an odd function. If you integrate the whole, yes. This area and this area have exactly the same magnitude. Opposite signs, integrate. You may wonder, well, in the lecture notes, it says this equation is useful in determining if a vibrational transition is allowed for it. But actually, it's also useful for transition of the electron. It's useful for the transition of rotation or translation. So it's a general rule. So this simple equation is very useful. Whatever transition it is, you just plug in the dipole moment in the middle. If it's vibration of a diatomic molecule, you just put the dipole moment in the middle. And then you put the ground state here, excited state here, or vice versa. It doesn't matter, because we're looking at just real functions. All those are real functions. And then determine if this guy is 0 or not. If it's 0, the transition is forbidden. If it's non-zero, then the transition is allowed. That's simple. And there's another reason. I want to show you this so-called electronic transition rather than vibrational transition. It's because actually, believe me, this is actually easier than determining whether a vibrational transition is allowed or forbidden. I still want to show you this vibrational transition. Yeah, we usually go from the easy ones to more complicated ones. Now you're going to see this. You're going to see this. When we do vibration, it's extremely difficult to work on anharmonic oscillator. So let's still start with harmonic oscillator. And let's look at if the vibrational transition is allowed or forbidden from 0 to 1. So this is the unit spacing from 0 to 1. Let's say it's vibrational. Let's say this is harmonic. And harmonic means you have this equation, so it's harmonic. All right, I'm going to just give you the ground state. The ground state is e to the power negative half x squared. And the first excited state is x times e to the negative half x squared. Okay, they both should have a normalization factor, but we usually don't care. Again, we don't care. Those are just numbers. Those are just numbers. Constants. It's to normalize the function so that the probability will be 1 in the whole universe. All right. And again, we look at HCl. And the bond distance between HCl at equilibrium, let's say it's x sub e. Okay, and we have the delta plus, delta minus. All right. Now, we need to decide whether the transition is allowed or forbidden. How do we do this? Simple. We first write out the integral. I'm sorry, it's it will look ugly at the beginning, but I will simplify it. Okay. So first, the integral d tau. The nice thing about this problem is we are only looking at just one dimension. Let's assume this HCl just vibrates in one dimension. So that's nice. At least it's a single variable problem. And again, you need to have psi naught in the integral. You have to include psi 1 in the integral. Okay? And the complex conjugate of a real function is itself. So we don't worry about that. And we just put those in. So either way, you can put excited state or left or right, because it's multiplication. It really doesn't matter for this case. And then you put mu in the middle. The dipole moment of this diatomic molecule. See, when you're looking at diatomic molecule, the dipole moment is defined in a way it's pointing from positive to negative. Right? Do you remember what's the way of direction of dipole moment? In nearly all textbooks, it's from positive to negative. But the other day, I checked this IUPAC UPAC calculation. It's from negative to positive. Oh, don't worry about it. That was the direction is correct. It's kind of strange. It's kind of strange. Anyway, you still need to write out the mu. So mu is proportional to the charge. Either delta plus or delta minus, they have exactly the same number, but opposite signs. Okay, I just put delta here. Delta. That's the charge, okay? Multiply by, how do you get dipole moment if you have the charge? And you need the distance between these two, right? Makes sense, right? Distance between each cell. Let's see. Right? But then this x sub e is just the equilibrium on distance. You haven't taken the vibration into account. Now you take vibration into account. So this x can be a variable. You know, the displacement can be positive, can be negative. When this HCl oscillates, the bond distance can be greater than x sub e, can be smaller than x sub e, right? So, vibration. keep this in mind, this guy is a constant. Okay, this guy is a constant, X of the use. Any questions so far? Delta is a constant, so I put delta here. Delta is the partial charge on hydrogen or chlorine. Any questions so far? And now I have to separate this term, this big integral into two integrals. One with xe in the middle, one with x in the middle. Okay, remember, keep this in mind, we have two terms. But I'm going to just do this xe in the middle. And quickly evaluate whether this is going to be 0 or not. Put a question mark here. And what do you think? This xe is a constant. And the function will be just x. Is that odd function of x or even function of x? If you change the sign of x, so now you're looking at this x as a function. As a function, x is a function of x, right? Okay, you can say that, right? X is a function of x. If you change the variable x, if you change the sign of the variable x, does the function x change its sign? Yes, so it's odd function. Odd. X is an odd function. X squared is an even function. Make sense? Okay. How about 1 over x? Even function or odd function? It's an odd function. How about x plus 1? Even function or odd function? X plus 1? Neither. Neither. X squared plus 1? Neither. X squared plus x to the power of 4. X to the power of 2 plus x to the power of 4. Change the sign of x. Even. X plus x cubed. Odd. Sine x. Odd. Cosine x. Cosine x peaks at x equals 0. Cosine 0 is 1. If So anyway, odd, even. How about constant? Even or odd? If I change the value of x, if I change the sign of x, how does this constant change? It's a constant. Actually, I just put a constant here. You can do that. I leave it in the middle because later I do x, so I leave it in the middle. So this is actually even and this is even. So in the end, what I'm looking at, an odd function in the middle or an even function. Negative, positive, positive, positive. So in the end, the product will be an even function or odd function. Well, the trick is, again, whenever you see odd function, put -1 and do the product. The product of -1 and all this is -1. So in the middle, it's an odd function. Okay. All right, that's the trick. If you see, a product of many functions, if it's an odd function, you see an odd function -1. See an even function +1, and then you take the product of all those -1 and +1s. In the end, if you get -1, that's an odd function. It's +1, it's even function. So what's the integral? What's the value of the integral? 0. Okay, very good. That's 0. So we only handle this term. Now we are going to handle this term, displacement. Okay. First, you have to understand this part. This is going to be 0 because you have odd function, even function, even function, even function. Multiply all those together, you get odd function. And because it's from negative infinity to positive infinity, it's anti-symmetric. And in the end, area in the positive region cancel with the area in the negative region. So in the end, the total integral value will be 0. So it's true, that's 0. So any question about that part? Yes?
Yeah, what happened to the x that was with the x?
Oh yeah, I'll do x right now.
Well, you used, what was the
right now,
there?
because it's in the middle, there were two terms, xe plus x. I was just mentally separate this table. I do this xe first, and then I'll do x.
Okay.
So, remember we had this, right? We had this. So I was doing this, and then I will do that, and then I will sum it up. Okay, so I'm going to do x, and then I'm going to sum it up. So first that xe will give you 0. So how about this guy? This x is also an odd function. So is this whole thing an even function or odd function? Yeah, it's even. It's even. You have odd, even. -1, +1, -1, +1. The product will be +1. Even function. And then this is going to be 0 or non-zero. Non-zero. It's going to be positive. It's going to be positive. Again, because this x multiplied this x, you get x squared, that's positive. You get this Gaussian function, this Gaussian function. They're all positive. You're integrating a function which is always positive. I'm going to draw the function here. It's going to look like this. Positive, positive. Oh, why is 0 in the middle? Because I think we have this x squared here. So at x equals 0, the function value should be 0. And it starts to increase as x increases, and then it drops down because when x approaches infinity, this whole thing approaches 0, faster than this guy. So the shape is like that. And if you integrate this part and this part, they're both positive. They're both positive. You sum it up, it's non-zero. Okay? And then remember, we have two terms. We have xe plus x. Okay? And one term will be 0. The second term, non-zero, so in the end, it's non-zero. So in the end, we just proved that the vibrational transition from level 0 to level 1 is allowed. So that's the conclusion. The conclusion is the vibrational transition of HCl from level 0 to level 1 is indeed allowed. And this displacement is quite important. All right, so I'll give you a different example.